Let's continue from where we left last class. We got introduced to poles and zeros, and the poles and zeros in the z plane is no different from the concept of poles and zeros that you had encountered in the Laplace transform case. And one difference is we are going to call poles or zeros at z equal to 0 as trivial poles or zeros, and we will see why they are called trivial poles or zeros when we later look at frequency response. And we saw some examples of systems having poles and zeros, and we also introduced the concept of poles or zeros at infinity. And the example that we had looked at towards the end of last class was this. We had each of n to be 1 over n for n between 0 to cap n minus 1, and then the corresponding h of z, if you apply the straightforward definition, it is 1 plus z inverse plus z power minus 2 all the way up to z power minus n minus 1, and this can be written as 1 over n 1 minus z to the minus cap n by 1 minus z inverse. And in terms of pole zero plots, there is a pole at, we also saw that there is an n minus 1th order trivial pole, and the remaining roots are the zeros of the transfer function, and they are the nth roots of unity. And if you take as an example cap n equals 8, you will have 8 zeros distributed on the unit circle uniformly. Therefore, here you will have a 0 at z equal to 1, and these are the remaining zeros. And we pointed out that at z equal to 1, there is a pole 0 cancellation. And we made the remark that if there were an uncancelled non-trivial pole in the transfer function, the corresponding inverse Z transform will have a factor of the form k by 1 minus a z inverse. And if you have a factor of the form k by 1 minus a z inverse, the inverse transform depending upon the ROC will either be of the form a to the n u of n or minus a to the n u of minus n minus 1. In either case, it is an exponential that lasts forever. It is a one-sided exponential that is of infinite duration. Therefore, if you had an uncancelled non-trivial pole, it will give rise to an exponential that is of infinite duration or semi-infinite duration. Either it will be right-sided or left-sided. So, moment you have such a component in the impulse response, such a system cannot be FIR. Whereas the system given here is indeed FIR. And in this form, a pole appears at z equal to 1, it has to necessarily get eventually cancelled. And to see the connection between this and the equation that we had written earlier, where we had taken this exact same system and then we wrote it in two different forms. One was the non-recursive form, the other was the recursive form. So, to see the connection between that and this, h of z is after all y of z by x of z. We have not formally introduced the notion of transfer function yet, but this is similar to what was happening in the Laplace transform case, where you have h of s is nothing but y of s over x of s. So, drawing upon that analogy, h of z can be thought of as the system transfer function, which in turn is y of z over x of z, and this is 1 over n 1 minus z to the minus n by 1 minus z inverse. And if you cross multiply you have this times x of z After we are done with this, we are going to look at properties of Z transform, and after linearity, the second property we are going to look at is the delay property. So, I will make use of that property now and write this in the time domain, and very soon you will be able to see why this is indeed true. So, if you take the inverse Z transform and write the above in the time domain, this can be written as y of n minus y of n minus 1, this equals 1 over n x of n minus 1 over n x of n minus cap n, and this follows from the delay property. So, this will be seen very soon. So, assuming for the moment that this is indeed true, you get this, and rearranging this, we can see that this is exactly the same equation that we had seen earlier. So, this is y of n is nothing but y of n minus 1. So, we were expressing the endpoint average as an update over the previous average. Take the previous average, add in the newest sample, and then subtract out the oldest sample. So, this is indeed the recursive implementation of the non-recursive system, and this follows as the inverse Z transform of the expression given here. And now you are able to see that if you have an FIR system and then if you implement it in a recursive manner, moment you have recursion, you will introduce poles, but the system is indeed FIR, therefore, the introduced pole cannot be uncancelled. Here in this case, the introduced pole is at z equal to 1, it is going to get cancelled by the 0 at z equal to 1. And one advantage of this is that it has fewer additions. The recursive implementation has fewer additions. You might wonder why you need to implement it like this rather than taking n samples and averaging all the time. You have fewer additions in this recursive implementation.